Welcome to the Deep Dive, the show engineered to cut through the noise and deliver the essential knowledge you need to be truly well-informed. Today, we're embarking on a fascinating journey into something that touches every single one of us, every single day, the very air we breathe inside our buildings. And maybe more surprisingly, how those buildings themselves can be designed to breathe right alongside us. Think about it for a second. Our built environment is incredibly energy hungry. Just making our indoor spaces comfortable, heating them, cooling them, ensuring good air quality, it demands an astonishing amount of power. The numbers are, well, frankly staggering. If you look back, say, to 2009, U.S. residential buildings alone were just guzzling 39% of our primary energy simply to condition indoor spaces. That's huge. And if we zoom out to the broader economic picture, between 1970 and 2005, energy spending in the USA, adjusted for inflation, it shot up by a whopping 250%. Escalating from around $83 billion to a full $1 trillion. This isn't just about comfort anymore, is it? It's about urgent economic and environmental imperative to conserve energy and drastically cut CO2 emissions. So what's the ingenious solution we're diving into today? Well, it's the profound, yet often underutilized, world of natural ventilation. We're going to draw heavily on the profound insights from Ulrike Passe and Francine Battaglia's foundational work designing spaces for natural ventilation. But we're also going to explore how this sort of ancient wisdom is being powerfully amplified by cutting-edge materials like phase change materials or PCMs. We'll pull some insights there from works like Hafiz Ali's phase change materials for thermal energy management and storage. Our mission today is really to unpack how rethinking space itself can transform buildings into dynamic, responsive entities that work with nature, not against it, allowing them to truly breathe and even, regulate their own temperature.
And that's exactly the journey we're on. It's interesting because for far too long, the design of natural ventilation systems has been sort of caught in this confusing middle ground. On one side, you had architects relying on what you might call magic arrow sketches, those broad conceptual strokes of an idea for airflow, almost hopeful thinking sometimes. And then on the other side, you had engineers grappling with incredibly complex finite difference computations, is essentially highly detailed mathematical models. They break space into tiny pieces to try and predict airflow. And this disconnect, well, it often led to a lot of confusion and maybe a general underestimation of what natural ventilation could realistically achieve. But this deep dive, guided by the very resources you mentioned, it really aims to provide a clear, useful guide, highlighting how designers can achieve truly low-energy, low-carbon buildings by embracing these passive strategies. And what's truly fascinating here is realizing that natural ventilation isn't just some interesting alternative. It's absolutely crucial for our global journey towards net zero energy consumption, and it's vital for carbon mitigation. So our overarching mission today is to discover how these passive design strategies, especially natural ventilation, can dramatically reduce peak energy loads, how they can vastly improve thermal comfort for occupants, and create genuinely healthier indoor environments. And like you said, we'll go a step further, exploring how they're integrating with and being, well, supercharged by exciting emerging technologies, particularly phase change materials, which, in essence, they act like thermal batteries, right?
Right.
Right within the very fabric of a building, offering this whole new dimension to thermal regulation.
All right, let's unpack this core problem a bit more deeply then. When we talk about buildings as major energy consumers, the sheer scale is it's daunting. The source highlights what it calls wasteful consumption, basically, expending massive amounts of energy to condition outdoor air, just to achieve a basic level of thermal comfort and maybe decent indoor air quality. It's an enormous drain on our resources, both economic and environmental. We've seen this consistent, steep upward trend in energy consumption in the United States. It soared from, 32 quadrillion BTUs back in 1949 to a staggering 102 quadrillion BTUs by 2007. And frankly, there's no real prediction of it declining significantly anytime soon, not without a fundamental shift in how we build. Let's just imagine for a moment. What if we could drastically cut this consumption? Not by adding more complex energy-intensive mechanical systems, but by fundamentally changing the very way we design our buildings. What if the building itself could become the primary environmental modulator, an active participant in maintaining comfort? It's a really profound shift in perspective, isn't it?
It really is. And here's where it gets really interesting. And it's a crucial distinction, I think. It's not just about flipping off lights or unplugging devices, right? It's profoundly about the air itself and our relationship with it. Ventilation, at its core, is simply the process of introducing fresh, high-quality outdoor air into a space, while simultaneously extracting the stale, polluted, or odorous air. Now, there's a very common misconception that we ventilate primarily to replenish oxygen. And yeah, fresh air does bring oxygen, but, unless you're stuck in an incredibly sealed environment like a submarine for days on end, people generally won't run out of oxygen in a typical building. That's actually a relatively minor concern, surprisingly. The real critical issue, and often the underestimated one, is diluting CO2. Carbon dioxide. Elevated CO2 levels, even those not immediately dangerous to life, can indeed cause drowsiness, reduced cognitive function, and just make the air feel heavy, hot, and unpleasant. Stuffy, right? So while we might not suffocate without proper ventilation, the air quality rapidly deteriorates, and that directly impacts our productivity and well-being. And crucially, ventilation's primary role is actually much broader. It adjusts humidity, it removes excess heat generated by people or equipment, it dissipates body odors, and very importantly, it flushes out emissions from the building materials themselves, those volatile organic compounds or VOCs. These VOCs can off-gas from paints, carpets, furniture, all sorts of products, and they are significant health concerns, much more so than a simple lack of oxygen. So what this all points to is that natural driving forces like wind and temperature differences, they're an incredibly underutilized design strategy. Yes, they're dynamic, they're always changing, which presents challenges, absolutely, but it also presents immense opportunities for truly responsive architecture.
So this begs the question then. What does this all mean for the architects and designers who are actually tasked with creating these spaces? It presents a truly fascinating paradox, doesn't it? Unlike, say, an airplane wing, which is meticulously designed to reduce resistance against air, let it flow smoothly, a building designed for optimal natural ventilation actually needs to, well, build up resistance to air. It's about orchestrating that resistance, intentionally shaping the flow, guiding the air precisely where you want it and at the right speed. It's not about fighting the air. It's more like dancing with it. Essentially, space itself must be composed in such a way that it strategically creates a pressure difference between two sides of a building. You need a high-pressure zone on one side, a low-pressure zone on the other. And of course, there needs to be a clear, unobstructed connection and opening, basically between those two sides, to allow just the right amount of air to flow through. The real genius, I suppose, comes in how designers can then subtly alter this flow. They can change the size of openings or their direction to fine-tune the airflow, make it faster, slower, redirect it. And here's a key insight that's often overlooked, apparently. The height of the space is absolutely crucial for driving effective airflow, especially with stack effect. So when we think about interior space, it has to be conceived to manage more than just one static, climatic, or seasonal condition. It needs to be adaptable. This means designers need to develop what the book calls an iterative parameter matrix, a structured, systematic way of repeatedly refining design choices and testing different variables. And focusing on volumetric proportions, thinking about the building as a three-dimensional volume of air to be sculpted, rather than just, a flat two-dimensional plan or mere numbers on a spreadsheet. It's truly about sculpting the air itself.
Yeah, exactly. And let's connect this to the bigger picture. This raises an important question, right? How do we, as designers, make air, which is inherently invisible? How do we make it something we can actually design for and visualize its movement? Louis Kahn's Esherick House, built back in 1961 in Chestnut Hill, Pennsylvania, provides a prime early example of this kind of masterful approach. Its spatial composition is quite remarkable. Kahn connected two single-height spaces and one double-height space, all within this deceptively compact volume. And Kahn, with incredible foresight and frankly poetic sensibility, didn't just design rooms. He intertwined structure, space, light, and even specific, thoughtfully placed vents, all designed to enhance what he called the immaterial movements of air and light. It's a beautiful phrase. And this profoundly changes the relationship between the inside and the outside, creating this dynamic living interior. In fact, modern computational fluid dynamics, or CFD analysis of the Esherick House, clearly highlights just how absolutely critical the height of that space is for effective stack effect cooling. It basically proves Kahn's intuitive genius with hard quantitative data, which is pretty cool. Now, thinking about the building skin, the facade, it acts as a really sophisticated filter. Consider something as seemingly simple as windows and their opening mechanisms. English sash windows, for example, they slide vertically, right? That allows for very gradual and controlled changes in opening size, and they don't protrude into the space, which is an advantage for managing airflow and just placing furniture. Hopper windows, which typically tilt inwards at the top, they're common in Nordic countries, and they demonstrate how daylighting and ventilation requirements can lead to really distinct window sizing and operational strategies. Different needs, different solutions. And the orientation of these windows in relation to the prevailing wind direction is also critical. It's fundamental. It directly determines the flow direction inside the space and significantly affects how well fresh air can mix with the existing indoor air. And it's often overlooked, I think, but external elements attached to the facade can significantly alter airflow patterns and velocity, both at the inlet and the outlet. Things like solar shading, deep overhangs, balconies, bay windows, even simple bug screens can create more complex, turbulent wind patterns around the building. And this makes evaluating a natural ventilation strategy far more challenging than it might seem from a simple diagram. And here's a truly counterintuitive concept that I think could revolutionize facade design. The idea of rough surfaces increasing speed. It sounds wrong, doesn't it? But think about a golf ball. Its dimples cause the airflow on its upstream side to transition from a smooth laminar flow to a more turbulent one. This turbulent boundary layer stays attached to the ball's surface much longer than a smooth laminar one would. This results in a narrower, low-pressure wake behind the ball and thus significantly less pressure drag, so the ball travels further. Now, applying this to buildings, especially high-rise structures, strategically designed surface roughness, perhaps through textured facades or strategically placed fins, might similarly reduce drag, and maybe even increase the efficiency of natural ventilation in ways we're still actively exploring. It really opens up new frontiers for architectural expression and performance. Fascinating stuff.
Okay, let's unpack this further then. Now that we've considered how space can be composed to facilitate airflow, how do we actually leverage nature's fundamental forces, specifically temperature and wind, to make buildings truly breathe? Let's start with temperature-induced air movement, often called stack ventilation. This is a principle that's been understood and utilized by humans for centuries, really, long before we had the scientific models for it. The core idea is brilliantly simple. Hot air rises, we all know that. As it warms, it expands, becomes less dense, and therefore lighter than the cooler air around it. This difference in density, driven purely by temperature, directly leads to a pressure difference. It's based on the column of warmer air inside the building versus the cooler ambient temperature outside, and crucially, the height of that internal column of warm air. The higher that column and the greater the temperature difference, the stronger the effect. It creates a natural upward draft. To give you a sense of scale, the 1994 Building Research Establishment Digest, which is a key reference in building physics, stated that for each degree Celsius of temperature difference between inside and outside, approximately 0.04 pascals of pressure difference are created per meter of building height. It's not huge pressure, but it adds up over height. This continuous movement leads to what's known as a neutral plane, a critical point somewhere in the building's height where the pressure inside and outside equalize. Below this plane, cooler outside air is drawn in through lower openings. Above it, warmer indoor air is pushed out through upper openings. It's like the building itself becomes this giant natural exhaust fan, constantly exchanging air without any mechanical parts.
And what's just fascinating here is how ancient civilizations instinctively understood and applied these principles ages before we had scientific terms or advanced computations. Take caves, for example. I mean, they're perhaps the archetypal form of shelter, right? And they naturally leverage their great thermal mass, the sheer ability of the earth and rock to store large amounts of heat and the time lag of heat transfer, meaning it takes a long time for heat to move through them, so they stay relatively warmer in winter and cooler in summer. And early humans likely channeled air through these natural pressure differentials, intuitively using what we now call stack effect for comfort within these protective enclosures. Then you have the remarkable heron houses in southeast Anatolia, Turkey. These date back thousands of years. They're these distinctive domed structures, often built with mud bricks because, well, local timber was scarce. They feature a central opening right at the very apex of the roof, kind of like a North American tippy tent, mainly for smoke exhaust from central hearths. But their passive cooling strategies, based on their spatial geometries, are incredibly sophisticated. It wasn't just about smoke. It's generally agreed that these houses are significantly warmer in winter and cooler in summer than contemporary modern structures, and remarkably more energy efficient. They were ingeniously designed for hot, arid climates, often experiencing high solar insolation around 7 kilowatt hours per square meter per day. That's a lot of sun. It just demonstrates a deep, inherited understanding of local conditions and how to work with them, not against them. Imagine stepping inside one on a scorching summer day. The thick mud bricks would have soaked up the day's heat, releasing it slowly at night, while that central opening created this constant, gentle pull of air upwards, flushing out stale air and drawing in cooler, denser air from below, maybe even from shaded areas. It wasn't just efficient. It was literally a sanctuary from the heat. And we can't forget Palladio's villas like Villa Emo or Villa Trento a Custozza in the Veneto region of Italy from the 16th century. Andrea Palladio, the renowned architect, he ingeniously connected his grand living spaces to cool air sources, often in basements or sometimes even ancient, disused quarries nearby. By connecting the warmer interior air of the villa to the naturally cooler, denser air found in these subterranean spaces, a subtle pressure differential was created. This naturally caused air to move and cool the upper floors. It's brilliant. In a way, the very ground itself performed as a catcher of cooling energy, as the source puts it, a direct, large-scale precursor to modern ground-coupled cooling systems. These examples just showcase such a deep, intuitive understanding of fluid dynamics and thermal properties long before the math caught up.
Okay, now let's turn to the other main force, wind-induced air movement, or cross-ventilation. This is perhaps the most intuitive form of natural ventilation for many of us simply opening a window on one side of a room and another on the opposite side, creating a clear, unobstructed path for the air to flow directly through. We've all done it. However, there's a significant challenge with cross-ventilation that designers constantly grapple with. Wind is never perfectly steady, is it? Neither in its magnitude, how fast it's blowing, nor its direction. It gusts, it shifts. This constant variability makes it inherently difficult to predict exact air change rates, which is crucial for consistent thermal comfort and air quality. It makes modeling hard. That said, cross-ventilation can be incredibly effective when conditions are right, and it can also be combined with a local stack component to enhance overall airflow and maybe reliability. It's worth noting a practical design limitation often cited in the field, though, for cross-ventilation to be truly effective in cooling a space, especially one with moderate to high internal heat gains. The depth of the ventilation path is generally limited to about 5 times the height of the room. Beyond that, the airflow tends to lose its efficacy, becoming too weak to properly refresh the entire volume of air. So this means designing for cross-ventilation requires careful attention to the building footprint and the interior layout. You can't just have infinitely deep rooms expecting it to work.
Exactly. And if we connect this to the bigger picture, many traditional architectural forms also mastered wind-driven strategies with incredible sophistication. Take courtyards, for instance. They hold immense tectonic importance for the internal climate and are widely celebrated across diverse cultures for their ingenious natural cooling strategies. There's been a long-standing debate about whether the courtyard is a truly universal archetype, though. Research by Radin et al., for example, compared courtyard typologies in cooler climates like Scandinavia, where they might primarily create pockets of solar gain to warm the surrounding spaces, versus their distinct function in the Arabic world, where they are absolutely central to cooling strategies. Different climate, different primary function for the same basic form. Hassan Fathi, the renowned Egyptian architect who championed vernacular design, he famously claimed potential temperature drops of 10 to 20 degrees Celsius in courtyards. He called them a reservoir for coolness. Lovely phrase. And what's exciting is that this claim, which was often considered maybe anecdotal, was recently verified through rigorous field measurements by Ernest and Ford. They studied the double courtyard of the Casa de Pilatos in Seville, Spain, and their work demonstrated the significant convective cooling potential of these connected courtyards in hot and arid climates. It basically proved that traditional wisdom often holds profound scientific truth. The numbers backed it up. Then there are the distinctive wind catchers of Yazd, Iran, known locally as badgers. These are striking mud brick towers, often very tall, divided into internal chambers with vents that open in various combinations to capture prevailing winds at different heights. They look amazing. And they were often connected to complex systems of rooms and sometimes subterranean qanats, those ancient underground water channels and courtyards. It was a whole integrated system. Together, these features were remarkably effective at creating thermal comfort for the inhabitants. Now, while current comfort standards might differ from a historical reliance on sweating as a primary cooling strategy, these wind catchers provided robust convective evaporative heat loss based on wind velocity and facilitated cooling by evaporating sweat on occupant skin with the very dry air currents they channeled. Many are still in use today and are just considered a testament to brilliant climate-responsive design. And this brings us nicely to the vernacular revival happening now. Contemporary architects are increasingly looking back to traditional knowledge and typologies as a source of sustainable wisdom, and rightly so. Studio Mumbai, for example, an acclaimed architectural practice in India, with projects like the Palmyra House and Utsav House, they are explicitly drawing on traditional knowledge and typologies from places like Goa and Mumbai. They create these highly movable and permeable elements in their building facades, think large operable screens, levers, sliding walls, elements that are far better suited for for local climates than generic, mass-produced windows and fixed glass panels. This approach highlights a profound return to climate-responsive design, understanding that the wisdom of the past offers powerful, elegant, and often low-tech, sustainable solutions for the present, especially when combined with modern understanding and maybe some modern materials.
So, after all this discussion about buildings breathing naturally using wind and temperature, what does comfort even mean in a naturally ventilated building? Especially when we're not relying on a thermostat set to a single rigid temperature point, like 21 degrees Celsius or whatever. This really challenges our ingrained assumptions about thermal comfort, doesn't it? It's crucial to understand that it's not just about the air temperature floating around you. That's only part of the story. In fact, research clearly shows that the surface temperature of adjacent walls is as important, if not more important, for an occupant's perception of comfort. Think about standing next to a cold window in winter. Even if the air thermostat says the room is warm, you still feel that radiant cold, right? So just cooling the air around someone is only one piece of a much larger, more nuanced puzzle. And this brings us to the really revolutionary concept of the adaptive comfort standard. This model, significantly developed by pioneering researchers like Gail Brager, Richard Didier, and Fergus Nicole, is truly transformative because it's based on extensive field studies of actual buildings and their occupants in real-world scenarios, not just, theoretical experiments in controlled climate chambers. It's based on how people actually feel and behave. The core principle of this model is that it does not aim for a perfect thermal comfort number, but acknowledges adaptability, changeability, user control, and intuition, as well as responses to seasons and weather. It's about accepting that comfort isn't a fixed point, but a dynamic range, and that human beings are active participants in achieving their own comfort. We adapt.
Exactly, and this raises an important question. How does this adaptive comfort model empower occupants and ultimately create better, more resilient spaces? Well, the adaptive model, unlike more traditional static ones like HHRD 55 in its basic form, fully accepts and indeed embraces the dynamic relationship between the outdoor climate and desired indoor conditions. This means it allows for indoor air temperatures to rise naturally in summer as outdoor temperatures climb, which is a sensible approach, really, given how people instinctively adjust their clothing, their activity levels, and even just their expectations based on the season and the weather outside. It's about designing with human behavior, not against it. Studies by Didier and Brager have consistently shown that occupants in naturally ventilated buildings tend to be more tolerant of a wider range of temperatures compared to those in rigidly air-conditioned environments where the temperature is held constant. This points to a different kind of comfort, perhaps, one that embraces connection to the outside world and acknowledges our inherent ability to adapt. We also need to factor in metabolic rate, or MET, which quantifies the heat your body generates. Think someone exercising in a gym versus a person seated quietly at a desk. A person in a gym, for example, releases about 5 times more thermal energy than a seated person. It's a huge difference. So to feel comfortable, they would logically need a lower air temperature or perhaps increased air velocity, maybe from a ceiling fan or an open window, to facilitate heat removal through evaporation from the skin. Similarly, the CLO factor, which is simply a measure of how much your clothing insulates you, directly impacts your comfort range. A heavy winter coat, for instance, significantly alters your perception of temperature compared to light summer attire. Seems obvious, but standard models often assume fixed clothing levels. And Lisa Heschong, in her seminal work Thermal Delight in Architecture, introduces this beautiful idea of thermal delight, the sensory pleasure derived from thermal experiences, and how this profoundly influences social communities. It's not just physics, it's social. She points to the powerful social connections fostered by sitting around a crackling fireplace with hot tea on a cold evening. Or perhaps more universally, by lingering on a porch swing on a warm afternoon, where that gentle, self-generated breeze makes you feel comfortable even in the heat. That shared experience. She laments that the porch, as a vital communal space in many U.S. households, sadly began to disappear with the rise of widespread air conditioning, which enclosed us in these climate-controlled boxes, separating us. This suggests that thermal comfort isn't just about a number on a dial. It's deeply intertwined with our social interactions, our connection to nature, and the very delight we find in our environment. It's about more than just surviving the temperature, it's about thriving in it.
Okay, so let's bring this into the modern era. Let's unpack how these natural ventilation principles are being applied in large, complex, modern buildings today, often combined with innovative technologies, like those PCMs we mentioned. A fantastic and truly pioneering example is the Commerzbank headquarters in Frankfurt, Germany, completed back in 1997. This building was a true game changer, wasn't it? Famously known as Europe's tallest naturally ventilated building at the time. and it featured a sophisticated mixed-mode ventilation system, meaning it intelligently switches between natural and mechanical ventilation based on external conditions. It's not all or nothing. It's an incredible design, almost like a living organism. The building utilizes a double-skin facade, essentially 2 layers of glass with an air cavity between them. This acts as both a buffer against external weather and as a sophisticated ventilation duct, intelligently mediating between the exterior and interior. Its central atrium, soaring through the entire height of the building, functions as the building's lung, effectively driving vertical airflow throughout the structure, leveraging that powerful stack effect we talked about. And get this, it incorporates sky gardens on different levels, which aren't just aesthetic features, not just nice places for a coffee break. They create miniature microclimates within the tower and serve as crucial controlled air intakes, drawing fresh air deep into the building. The entire system is managed by a sophisticated building management system, or BMS, basically the building's central nervous system. It integrates hundreds of sensors to control the facade openings based on real-time data like wind speed and direction, outdoor temperature, and even rain detection. This intelligent, responsive control allows the building to achieve remarkably low CO2 emissions and significantly reduced energy consumption compared to a conventionally air-conditioned skyscraper. It truly breathes with the city, demonstrating what's possible even at a grand scale.
Yeah, Commerzbank was definitely a landmark. And what's fascinating is how these modern projects keep pushing the boundaries, often combining multiple passive strategies in really sophisticated ways. The KfW West Arcade, also in Frankfurt, completed in 2010, is another prime example, clearly building on the lessons learned from Commerzbank. It's characterized as a hybrid system where, again, the outer skin acts as a buffer and ventilation duct. But what's particularly innovative here is how thermal mass is used to balance the temperature swings. This is key. This means the exposed concrete structure itself, the floors and ceilings, are designed to absorb and release heat slowly throughout the day and night. This dampens extreme temperature fluctuations and creates a much more stable, comfortable indoor environment passively. This building cleverly integrates natural ventilation with highly efficient mechanical systems. It's not purely passive. For example, it uses cross-ventilation in its library section via a dedicated ventilation skin, but it also incorporates advanced strategies like its night flush cooling strategy. This is really interesting. This relies on an extreme airtight building envelope. You have to minimize uncontrolled air leakage for this to work well on those exposed concrete slabs. The principle is elegantly simple. During cool nights, automated openings allow direct night ventilation to passively cool down the massive concrete structure of the building. The high heat capacity of this thermal mass allows the building fabric to soak up heat gains throughout the following day, preventing the indoor air from warming up too quickly. It's like storing coolness in the building's very bones overnight. And this is where we see that truly cutting-edge integration of advanced materials you mentioned earlier. Phase change materials are also added to store latent heat. So think of PCMs as these sophisticated thermal batteries embedded within the building's fabric, maybe in wall panels or ceiling tiles. Unlike conventional thermal mass like concrete, which simply absorbs sensible heat, meaning its temperature changes, PCMs absorb and release a large amount of heat when they transition between solid and liquid states, or vice versa, all while staying at a relatively constant temperature. It's latent heat. For instance, a specific PCM might be designed to melt at, say, 23 degrees Celsius, around 73 Fahrenheit. As it melts, it absorbs a huge amount of heat from the room, thus keeping the surrounding space cool without its own temperature rising much. Then, as the evening temperatures drop below 23°C, it solidifies again and releases that stored heat back into the space. This latent heat storage significantly enhances the building's ability to manage temperature swings and reduce peak cooling loads. It works in powerful synergy with the conventional thermal mass and the night ventilation strategy. It's a fantastic combination. The KfW West Arcade also uses ground-coupled heat pumps through energy piles embedded deep in the ground for additional, very efficient summer cooling and winter heating. It really demonstrates a truly integrated, multi-layered approach to passive and low-energy design. And the energy data is incredibly impressive. Monitoring revealed that ventilation alone provided close to 50% of the cooling energy required, saving a remarkable 84% compared to typical fully air-conditioned German office buildings. That's huge savings. It's just a testament to the power of a truly hybrid passive approach, intelligently combining strategies. And there are other notable examples that showcase a range of brilliant strategies too. Judson University in Elgin, Illinois, effectively uses vertical stack spaces for both ventilation and day lighting. They even incorporated photovoltaic arrays on top to deliberately warm the stack air and increase the pressure differential, intensifying the natural chimney effect. clever. The Lycée Charles de Gaulle in Damascus uses solar chimneys, basically black painted stacks, strategically heating the top of the stack with the sun's radiation to enhance the stack effect and pull air through the building. And the Habitat Research and Development Center, HRDC, in Windhoek, Namibia, features distinctive wind towers, very reminiscent of traditional designs like the Iranian Badgers, to harness wind for cooling in a very hot climate. These are all just testaments to the power of thoughtful, integrated, passive design that learns from the past and innovates for the future.
So, after exploring these incredible breathing buildings, both ancient and modern, and seeing these complex integrations, how do designers actually predict and optimize these invisible air movements within a building before it's even built? How do they ensure that the air will flow as intended, especially with these hybrid systems? This is where the science really steps in, offering a suite of powerful tools. There are various scientific approaches to studying ventilation, ranging from relatively simple small-scale and full-scale experiments in wind tunnels or actual buildings, which can be quite costly and time-consuming, actually, to empirical and analytical models that use simplified equations to approximate airflow. Useful, but limited. Then there are multi-zone and zonal models, which offer increasing complexity, dividing a building into interconnected zones. Better, but still simplified. But the most sophisticated and visually impactful approach, and one that has truly revolutionized climate-responsive design in recent decades, is computational fluid dynamics, or CFD. CFD is this powerful computational tool because it calculates essential parameters like air velocity, pressure, and heat transfer within a building with astonishing detail. And crucially, as you mentioned with the Ishak House, it helps us visualize the airflow patterns in a way that's just impossible with the naked eye. Imagine creating a digital wind tunnel right inside your computer. CFD allows you to literally see how the air swirls around a chair, or how much fresh air actually reaches someone sitting at the back of the room, or how a specific window opening might create an undesirable draft. It effectively turns the invisible into something that designers can see, analyze, and manipulate, moving beyond pure intuition to something approaching scientific precision in airflow design.
Yeah, it's an incredibly powerful tool, but this raises an important question, and it's one that often comes up, quite rightly. How accurate can these incredibly complex simulations really be? It's true that even with the fastest supercomputers available today, computation-intensive calculations for turbulent flow fields, that chaotic, swirling movement of air we experience, remain a significant challenge. The sheer complexity means that, fundamentally, all solutions that are obtained for turbulent flow fields are approximations. We have to remember that. We're always dealing with powerful models that approximate reality, not perfect representations. However, they're incredibly robust when used correctly, and they're constantly being validated against real-world data, providing invaluable insights for designers. The core of CFD works through this process called discretization. Fancy word, simple concept. It means taking a large volume of space, like an entire room or even a multi-story building, and conceptually dividing it into hundreds of thousands or even millions of tiny microscopic grid cells. For each one of these tiny volumes, the basic laws of physics, the conservation of mass, momentum, and energy are solved using complex mathematical equations, iteratively. This iterative process then builds up a detailed picture of the pressure, velocity, and temperature fields within that tiny cell, and by extension across the entire space, giving us a comprehensive understanding of the overall fluid motion and heat transfer. It's like building a pixel by pixel, but for airflow. Accurate modeling also hinges completely on defining precise boundary conditions. What's happening at the edges of your model? For instance, at walls, we typically use a no-slip boundary condition, which means the fluid velocity is assumed to be zero right at the surface of the wall. That's an important physical reality. For openings, like windows or vents, you can prescribe external conditions like wind velocity and temperature based on weather data. Or, if the velocity isn't known for sure, you can model it by prescribing the outdoor ambient pressure and temperature, allowing the simulation itself to determine the airflow direction and speed. And here's a concept that really guides the cutting edge of this design, particularly when combining natural ventilation with other passive strategies like PCMs or thermal mass. Predictive controls. It's like that famous quote from the hockey player Wayne Gretzky, "I skate to where the puck is going to be, not where it has been." In the context of building controls, this means the intelligent building management system can anticipate future changes in natural heating and cooling needs rather than just reacting passively to current indoor conditions. It looks ahead. For example, the indoor heating rate of a building can be described mathematically, considering dynamic factors like outside temperature, solar radiative heating coming through windows, and wind speed affecting infiltration. The coefficients in this equation relate directly to the building's thermal mass, how quickly it absorbs or releases heat, and how it interacts with those external changes. By understanding these dynamics, and crucially, by predicting future weather patterns using advanced meteorological forecasts, which are getting better all the time, designers can program sophisticated controls. For example, a predictive system might see a sunny, hot forecast for tomorrow, know your building's thermal mass properties and the melting points of your integrated PCMs, and decide to start a night flush cooling cycle tonight, actively preparing the building fabric to absorb tomorrow's anticipated heat before it even arrives, essentially pre-cooling the building structure and the PCM thermal batteries. This makes buildings truly intelligent and incredibly responsive to their environment, optimizing comfort and minimizing energy use proactively.
That concept of predictive controls, of buildings actually thinking ahead, is truly compelling, isn't it? But let's pivot slightly. What stands out to you as the biggest hurdle for wider adoption of these sophisticated natural ventilation strategies, especially when integrated with other passive elements like PCMs? It seems like there's incredible potential, but also real-world challenges, particularly in our increasingly dense urban environments. Well, one major impact is urban climatology. We often don't think of individual buildings as affecting the weather, but collectively, they absolutely do. Buildings act as massive obstacles within a city, profoundly influencing local wind patterns, creating turbulence, slowing down breezes. This not only reduces the potential for effective natural ventilation in dense urban contexts, but also significantly contributes to the urban heat island, UHI effect. That's where temperature differences between the city center and the surrounding rural areas are dramatically amplified. The city becomes much hotter. This means our buildings are both sources of waste heat and consumers of cooling energy within the urban landscape, creating this kind of feedback loop that just exacerbates the problem. And another specific challenge arises in what are called street canyons, those deep, narrow urban streets lined with tall buildings. Because of the complex shifting patterns of air movement and potential flow reversals within these canyons where wind can swirl unpredictably, sometimes even flowing opposite to the prevailing wind direction above the roofs. Vents in urban buildings often need to be meticulously designed to function as both inlets and outlets, or at least be able to dynamically adjust to account for constantly changing wind directions and pressures at street level. This inherent unpredictability, combined with the sheer number of design variables we've talked about, reinforces the immense complexity of choices involved in designing for natural ventilation, especially when dealing with such dynamic variations in the urban fabric. It's definitely not a simple one-size-fits-all solution, is it? It requires deep understanding and sophisticated tools like CFD to get it right.
Absolutely. And if we connect this to the bigger picture, the future truly demands a sophisticated blend of knowledge. It has to draw from both ancient wisdom and cutting-edge science. You touched on it perfectly. Predicting exact air change rates for wind-induced ventilation is inherently difficult, precisely because of the unsteady nature of wind. It's a dynamic force, not a constant, predictable one. This necessitates resilient design strategies, ones that can cope with variability. And this is why the path forward, I believe, must involve combining that traditional, inherited architectural wisdom, the lessons from Herrenhauses, courtyards, and wind catchers, which implicitly understood these principles through centuries of trial and error, combining that with contemporary scientific methods and advanced computational tools like CFD. These tools help us verify the actual performance of these inherited concepts in a modern context, ensuring they work effectively today and into the future. They let us quantify the intuition. It's about leveraging thousands of years of human experience with cutting-edge analytical power to mitigate those uncertainties and optimize performance. Ultimately, the most robust, resilient, and energy-efficient path forward lies in the approach of combining different passive strategies, what we've been calling hybrid passive strategies. We've seen how natural ventilation can be integrated with significant thermal mass, like the exposed concrete slabs in the KfW Westercade, which absorb and release sensible heat. And, as we discussed, the strategic integration of advanced materials, like phase change materials, which store and release latent heat with incredible efficiency, further enhances this synergy. Imagine naturally ventilated walls or ceiling panels integrated with PCMs, constantly working passively to maintain comfort by absorbing heat during the day and releasing it at night. This combined, multi-layered, hybrid passive approach offers the most robust, adaptable, and truly sustainable solution for buildings moving forward, allowing them to effectively store and release thermal energy reducing reliance on mechanical systems to an unprecedented degree, maybe even eliminating it in some climates or building types.
So what does this all mean for you, our listener? Whether you're an architect sketching a new building, an engineer crunching the numbers, a sustainability professional charting a greener path, or maybe just someone curious about the future of our built environment. Well, it means that by truly understanding and working with natural forces, not against them, buildings can become truly responsive, dynamic entities. Entities that dramatically reduce energy consumption and profoundly enhance human well-being. We've explored how natural ventilation, when integrated thoughtfully with other passive elements like high thermal mass and even advanced materials like phase change materials acting as thermal batteries, how this combination is not just about saving energy, as important as that is. It's about creating more comfortable, healthier, and frankly more delightful spaces for all of us to live, work, and thrive in. These aren't just technical solutions. They're about reestablishing a profound, maybe long-lost connection between our built environment and the natural world around us.
Yeah, exactly. And this raises an important final question for you to consider. What will your next space feel like? What do you want it to feel like? Hybrid passive strategies blending the ancient art of natural ventilation with the modern science of materials like PCMs and sophisticated controls. These are not just an option for energy efficient design anymore. They are, I think we can safely say, the undeniable future of sustainable architecture. So we encourage you to look at the buildings around you differently now. As you walk down the street, as you sit in your office or home, consider how they breathe, or maybe how they don't breathe, how they interact with their environment, and how they contribute or detract from your comfort and health. The journey to net zero energy buildings is deeply intertwined with a renewed appreciation for how intelligent, nature-inspired design can truly unlock the immense power of our environment for our benefit.